In this presentation, we'll look at Big O notation. This presentation is being done by group members CJ, Kevin, and Matthew for the CPS 162 Spring 2021 class. So what does Big O mean? Well, contrary to some commercials that were on TV a few years ago, it's not for Overstock.com. Big O is also not talking about that scene from Office Space. When we talk about Big O notation, really we're talking about a program's efficiency. Now, there's really two different ways to measure efficiency for a program. We could be talking about the space or the memory that it takes a program to run, or we could be talking about the amount of time it takes a program to run. Those are two different competing interests, meaning that, well, if we want to decrease the amount of memory, it's going to take more time. Or if we want to decrease the amount of time, it's going to take more memory. When we talk about Big O notation, generally we'll be looking at the amount of time it takes for a program to run, but really it's that measure of efficiency. So what does Big O measure? Well, it's really measuring the number of steps in that program. When we talk about measuring the number of steps, we're always talking about, well, how many steps would it take in that worst case scenario? So for a sorting algorithm, it's, well, if the data was in the worst possible arrangement, how many steps would it take? There is a way to think about the efficiency in terms of the best case scenario too, but generally when we talk about Big O, we're thinking of that worst case scenario. Let's look at a quick real world example. Suppose you're waiting in line for your order at the grocery store. There's different parts of the grocery store checkout process that correspond to different amounts of time. We have the parts of the process that are a fixed amount of time, no matter how big your order is. So for example, paying for your order with a credit card would always take the same amount of time, or swiping your Shoppers Club card would always take the same amount of time, no matter how big your order is. Other parts would be dependent on how big the order is. So for example, if you're looking at the amount of time it takes the cashier to scan items, that'll take longer as we have a larger order. How do we measure Big O? Well, it's always measured on the idea or the algorithm. It's never measured on a specific computer or processor speed. When we talk about Big O and measuring the efficiency of a program, it's always the conceptual efficiency. It's always based on the algorithm. It's not dependent on the language or our hardware. When we look at Big O notation in math, when we say a function g of n is Big O of f of n, it means that g of n is less than or equal to a constant times f of n for large values of n. What this is saying is our f of n function should be bigger than g of n, far down the road, far on the right-hand side. When we talk about Big O notation, we don't care what happens in the middle. So for example, x squared and 2 to the x, our function x squared actually is bigger in the middle for x values around 2 and 3. However, when we talk about the efficiency, we're really looking for, well, what's happening down the road? So in this case, our 2 to the n function grows much faster than our x squared function. So we'd say x squared is Big O of 2 to the n. In the next part, CJ will go through a couple of different algorithms and explain the Big O notation for that.
Big O notation. So our first example here is constant time. Now, although the array can vary, the output is constant. It is the first element in the array. So in terms of complexity, this is the simplest one. The second one here is ON, and that is represented in linear time in terms of complexity. Now, the array could be either 1 or it could be 1,000 elements. It really doesn't matter. But as you can see in the code itself, which is written in Python, it goes through the array n number of times and it prints it out. So this is one step above the constant time because it's in a linear fashion. The third one is quadratic time, O(n) to the second power, and it has an input of an array and an iteration. Now it has 2 for loops in here, so there's an added layer of complexity to it, and it'll go through the iteration n number of times printing out that array. So in terms of complexity, this is probably the higher one. We also have, in the next slide, we have linear search. So this search algorithm, its worst case scenario is linear time, while its best case scenario is constant. And I mean, we all know how linear search works. So it's just going through the array or whatever it is, whatever data structure it is in a linear fashion, and it's searching for the element. And those are the 2 outcomes for that. Now, in this example, I have the linear search we just went over compared to the binary search. And the worst case scenario for the binary search is logarithmic time, which has a higher complexity than the constant time. Compared to the linear search, the worst case scenario is worse than it was for linear search for this function, for this algorithm, but we have selection sort. And unlike the other 2, the worst and best case scenario are the same. So you have n to the second power. So the selection sort isn't any more efficient or inefficient. In terms of complexity, it's the same for the worst and best case scenario, unlike the other 2.
So another example of big O notation is O of 2 raised to the nth power. And basically what that means is this algorithm is growing exponentially. And so whenever you see this notation, think of recursion, because that's what leads to this specific notation. So in this specific example here, we have the algorithm used to solve for the Fibonacci sequence. So without getting too in-depth and too deep about what that means, right here in line 14, there is a recursion call. There's 2 of them. And so that's why this is O2 of n, because 2 is the number of recursion calls in the algorithm. And then n is how far deep or how many times we're repeating to find that final answer. So that's why we get O2 to the nth power. Another big O notation example is O log base 2 of n. So in this one, whenever you see this, think divide and conquering. And that's exactly what this algorithm is doing right now. The binary search. This one is dividing and conquering to find that one final answer. And although this one's using the positions to find the final answer, it's still the same idea of dividing and conquering. So right here, it's where it's being divided into 2 to find that final position. So the way you get O log base 2 of n is you're finding that one answer. You're looking for that one final answer. 1 is equal to the size n divided by 2, because you're dividing the whole size by 2 every time. But you don't know how many times you're going to be dividing by 2 to get that final one answer. So you do 2 raised to the x power. And so then to solve for x, with x being how many times you're going to be dividing by 2, you solve for x. So to solve for x, you multiply 2 to the x power on both sides. So you get 2 to the x power is equal to n, the size. And so then to get x, you take the log base 2 of both sides, and you get x is equal to log base 2 of n. And so what that means is that we're dividing by 2 x number of times. And that x number of times you find by doing the log base 2 of n. So that's how many times you're going to be dividing the array size to get that final answer. So whenever you're trying to find the big O notation of an algorithm, you always take the worst case scenario. So here's an example for you. So say you're looking for a photo in your phone gallery, and you decide to use a simple search technique, which is basically just you swiping through every single photo until you find the photo you're looking for. Best case scenario, you find it with just one swipe. There it is. But that won't be the case for every single photo. It'll be dependent on your number of photos, which is n, the size of the number of photos you have in your gallery. So that's why this simple search technique would be O of n, because it depends on the number of photos you have. You could be swiping n number of times until you find that photo. And the reason you say O of n for this simple search technique or algorithm is because you're saying that the algorithm won't be slower than O of n. It won't be faster than it, but it also won't be slower than that. So this right here, continue on with worst case scenario, this chart tells us how all the different notations compare to one another and how they rank from worst to best. So if an algorithm had O of 1 and had O of 2 raised to the nth power, you would neglect the O of 1 because the O of 2 of n is worse, so you want to declare that algorithm as O of 2 raised to the nth power. So let's put it all together. So how do you find the O notation of this algorithm right here, this function? So let's start with the first line right here. Right here is this variable is getting the value of the first element in the array. So regardless of what the size is, it's always going to be the first element. So this is going to be O of 1. This next for loop is going to be repeating n number of times. It's dependent on the size of the array. Doesn't matter what it's doing, it's just displaying the element, but it's still repeating n number of times. So this is going to be declared as O of n. Same with this one. It's repeating n number of times. This one, in this case, is adding up those values and storing it in sum, but it's repeating n number of times. So this is also O of n. This next one is a nested loop. So this one's repeating n times n squared, or times n number of times. So that's getting n squared. So this one will be declared as O of n squared. And so to get the final notation, what you want to do is add them up all together. So you have O of 1 plus n plus n plus n squared. And so you can see you can simplify more. So you get O of 1 plus 2n, because there's two n's, plus n squared. And so whenever you're solving for the O notation of a function or of an algorithm, you drop any constants. So you can drop the 2. So you get O of 1 plus n squared. And then, again, as we mentioned, you get the worst case scenario, or you drop any insignificant factors. So you get O of n squared as your final notation for this whole algorithm/function. So that's it. Hope you got an understanding of what big O notation is now, and you can use that now and look forward to using it in your future endeavors. So thank you for watching.